collision time delta t. So this is the time between subsequent collisions. And in order to interchange momentum between the particles, you sort them into cells, and in each of the cells, there happens the interchange of momentum by rotating the relative velocities of the individual particles with respect to the center of mass velocity of the whole cell. And you do this by choosing a rotation axis randomly for each of the cells. So each cell has a different rotation axis, and then you rotate the relative velocities. Choosing the rotation axis randomly guarantees you that you don't induce any external angular momentum, and it also ensures that you have molecular chaos. And because you just rotate the relative velocity, you have local momentum conservation. And regardless how you perform your collisions and how you do the rotations, local momentum conservation means that you have hydrodynamic interactions. Additionally, this method also locally conserves the energy, which enables, in this method, the transport of heat, and therefore the possibility to implement temperature gradient. And also an additional feature this method has is that it includes thermal fluctuation. That means local fluctuations of the temperature, but also of the density of particles in each of the collision boxes.
Excuse me, one question is, so you preserve angular momentum in average?
An average.
But locally, at some point, can happen that you don't preserve it?
Locally, you don't preserve it. And also this has some effects in cases when you have, for example, an external angular momentum imposed. Mm-hmm. This can happen, for example, if you have colloids which rotate in a magnetic field or so. Then it's important that you have local angular momentum.
Because I mean also when you have a gradient like here of temperature, when you rotate, of course, if it's kind of same isotropic, the system is no problem. You rotate here and you rotate here, it's kind of equivalent in the random rotation. And when you have kind of a gradient of temperature, how can you prove that that's kind of innocuous, the effect of the rotation, and then preserve things properly?
So this, in general, this does not disturb your system. There even exists corrections for this, so you can have a version of this multi-particle collision dynamics that locally conserves the angular momentum. But it's only required in certain cases. Okay, this method so far it has been used a lot it has a lot of applications which have been done for polymer systems, colloidal systems with external fields like shear flow, sedimentation, and even more complex molecules like star polymers and vesicles, or recently it's very successfully applied to the simulation of red blood cells. And you can also have many of them which you want to study in a capillary. But so far this method has been only used in isothermal conditions. But now we want to have a system with an inhomogeneous temperature. And we have tried to impose several boundary conditions, or several different methods to apply boundary conditions. And so first we have started to control the temperature by applying thermostats just at the boundaries of the of the system. And we have done this in combination with walls. But these walls, they have an effect on the hydrodynamic interactions in your system. So that was the reason for us to try a different method. And there we use open boundary conditions. That means we use a, so to say, biperiodic simulation box in which you have a repeated pattern of an increasing temperature towards the middle, and then you decrease again the temperature. We have used this method in order to have no additional effects of the walls to our system. And here is an example of how the temperature distribution in our system looks like. So we control the temperature here at the boundary, and in between we have a linear temperature gradient which evolves from itself, so to say. An additional effect that you have is that we will also have a density gradient in your system, because the equation of state for multi-particle collision dynamics is an ideal gas. And therefore this follows the ideal gas equation of state. And here you see that it has some small deviations from a linear behavior. But to the extent in which to the magnitude of the temperature gradients that we apply, you can assume that this is a linear density gradient. Okay, so one of the main reasons or the main motivations to study for our simulations were experiments with coated colloids that have been performed in Jülich by the group of Ning. And they studied the Thoré coefficient of a colloidal suspension with different volume fractions.
Can you comment a few more words on what kind of coated colloids those are?
Okay, the colloids, they had a coating of long changed molecules, not polymers, but octadecyl. I will come later to this point. So this is important for the interactions between the colloids.
And the size of those? Well, they're not monodisperse, or?
The size of the colloids, I think it was in 200 nanometers, but I'm not sure. But I want you first to focus on this region here, where you have a low volume fraction of colloids. And in this region you can basically assume that the interactions among the colloids are not important. But you observe, and what you observe in this region is that the temperature the average temperature of your solution has an important effect in which direction the particles will drift. So basically at low temperatures the particles drift to the hot side of the system. That means you have a negative Thoré coefficient. And at high temperatures they will start to drift to the opposite side, so to the cold region of the system. And this is only due to effects which come from the colloids with the solvent, so this is a single particle effect. But if you increase your volume fraction, then of course interaction among the colloids become important, and that's where this coating comes into play. Because this coating consists of long-chained molecules which sit on the surface, and they are coiled on the surface at low temperatures, and then you have an attractive interaction potential between the colloids due to the core of the colloids. When you increase the temperature, these molecules will extend on the surface and, so to say, screen the range of interaction, this attractive interaction range, and then these colloids behave like hard spheres. And what you find is that when you increase the volume fraction, that with different types of colloids, you will have a different collective behavior. So, in principle, you observe that for all colloids, if you increase the volume fraction, at some point the Thoré coefficient will start to decrease, and you can even induce a sign change so that they will also go to the other side of the system. But to study this effect of the different interactions, we subtract the contribution of the Thoré coefficient at 0 volume fraction. So that means we are left with the collective contribution to the Thoré coefficient, which stems from the colloid-colloid interaction. And here we observe that the attractive colloids, that they have a positive Thoré coefficient up to a certain volume fraction, and then they start to drift to the hot side of the system. And the hard sphere-like colloids, they have a negative Thoré coefficient, and then they start to, they also start to drift more strongly to the hot side of the system.
The attraction is due to what? Is the electric interaction, or what would make a difference?
So these polymers here which are shown, this is very exaggerated. In fact, they are very, very small compared to the size of the particle, so they only make up 0.1% of the particle size, and these interaction I think this is a chemical interaction with the surface.
So not a Van der Waals interaction?
Sorry?
It's not a Van der Waals interaction?
Yes, it's a Van der Waals interaction.
So there's any kind of entanglement between different colloids because chains are too short.
No, I think they may ensure that you have a stable suspension and that you don't have the particles stick together or something.
So the Van der Waals interaction is kind of the solvatation of the colloid by the solvent particles. I mean, what you describe like this range that you can screen or not is the solvent particles interacting with the colloidal particles, not colloidal particles.
No, the colloids among each other.
So what is the average distance between the colloids, just to have an idea concerning Van der Waals? What's the density of them?
I mean,
here the average distance between them.
Okay, I cannot tell you what is the average distance, so the volume fraction is up to 30%. So. Okay, and the first thing we wanted to study in our simulations were these collective effects, and we want to do this with a simulation model in which we take this into account explicitly with an interaction potential. So we describe our interaction of the colloid with the solvent with the multi-particle collision that I present you previously, and in these collisions where you just interchange momentum between the colloid and the solvent, this leads to a very small single particle Fourier coefficient. That means so that you basically have a setup in which you don't have to subtract this contribution anymore as we did previously with the experiments. And your Fourier coefficient basically only stems from collective contributions. And we use different types of interaction potentials to study effects of purely repulsive or attractive potentials with different ranges and strength.
And the big colloids and the solvents, so they can interpenetrate?
Yes, the solvent particles can interpenetrate here, and they interact here with the center of mass of the colloid, and yeah, this is where they interact.
So you cannot
in the respective collision cell of your simulation box.
You cannot have kind of a sort of potential or some kind of interaction that depletes the region where it's supposed to be the particle, the big particle.
Yes, you can do this, and we will do this in a later stage.
So these are two-dimensional simulations or 3D?
This is three-dimensional. Okay, so an example of a simulation where you measure the Fourier coefficient is shown here, and in the flux equation for the mass flux in the stationary state, the flux vanishes, and then you can express the Fourier coefficient, which is the ratio of these two transport coefficients, so dt divided by d. And this is then the ratio of the concentration gradient and the gradient of the temperature. And if you look at the density distribution of the individual components, which is shown here, you see here the solvent, and these are the colloidal particles. You can observe that here there are less colloids than solvent particles in the cold region of the system. And here this translates, so now if you plot the concentration, this here is a typo, this should be an X. So the concentration of colloidal particles increases towards the hot side of the system. And here is also the Fourier coefficient, which then means you have a negative Fourier coefficient. And this was just an example, and now we want to study different interaction potentials. So we use the Lennard-Jones potential, which is either purely repulsive or attractive. And what we find is that for the purely repulsive Lennard-Jones potential, you have a negative Fourier coefficient, that means a larger accumulation of colloids on the hot side of the system, and the magnitude of the Fourier coefficient increases with the volume fraction. And for attractive Lennard-Jones potential, we have a region where we have an accumulation of colloids on the cold side, but eventually, if the volume fraction gets more and more larger and the colloids can become closer and closer, then also the repulsive part of the potential comes into play, which drives then your suspension to the hot side of the system. So in principle, these repulsive interaction lead to a uniform distribution of colloidal particles. I mean, in the limit of close packing, then you would have the colloidal particles uniformly distributed in your system. You would have the gradient of the solvent, and then you have a higher concentration of colloids on the hot side. This is basically why it's here negative. But we find that just this, the appearance of this plot is similar to what we find in experiments. And in the next step, we wanted to study what's the effect of the interaction strength, where we use the potential that we named the sticky potential, which is much more short range than the Lennard-Jones potential, as it also is assumed to be with the colloidal particles. And then with different interaction strengths, we find that for with very attractive, so to say, very sticky colloids, we have a positive Fourier coefficient, and for the not so strong attractions, we have a negative Fourier coefficient, which is similar to the hard sphere-like colloids in experiments and the very sticky colloids. So in general, we have a trend that agrees with the experiment. So in the end, we were interested what is the origin of this behavior, and we tried to explain this. So our interpretation of these results is that if you express the Fourier coefficient, which is basically proportional to the gradient of concentration, you can also express it by the gradient of the individual density of the particles. And now, under the assumption that the components don't interact mutually, but just expand independently with respect to the temperature gradient, you can describe these ratios by the thermal expansion coefficients. And the thermal expansion coefficients for the solvent, which is that of an ideal gas, is well known, and also for the colloids, we use the hard sphere equation of state to compute this thermal expansion coefficient. And here, what you see here with these black lines are the difference of the two thermal expansion coefficients together with the simulation results. This CS here is for Carnahan-Starling, which is a very well established equation of state for the hard spheres. And we find that the simulations fit very well with these Fourier coefficient from independent thermal expansion. So these were the results for the collective Fourier coefficient. And now we want to study what is the effect of single particles with the solvent. Therefore, we use a simulation model in which we use an explicit interaction potential between the colloid and the solvent. And then you see here, opposite to the previous case, the particles cannot penetrate into the colloid anymore, but they are reflected at the surface. And the potential that we use here was again the Lennard-Jones potential, and we use repulsive and attractive potential just to see the basic effects of repulsion and attraction. And because we have a conservative potential, the reflection here at the surface is specular, and in this case the Stokes friction coefficient, which is also a well-known result, is 4 pi times the viscosity times the radius of the particle. Normally, when the colloids are reflected not in a specular way, but so to say reflected in the same direction as they came from, then you have 6 pi, the same result with 6 pi eta times r. So basically that means the fluid can slip along the surface of the particle, but normally you have the boundary condition that the velocity of the fluid is 0 at the solid boundary. in the reference frame of the colloid. But we use just this with these potential effects. This is an additional effect that you have, so to say. Okay. Now, if we want to study the Soré coefficient for a single colloid, we cannot, as we did previously, observe the concentration gradient anymore, because would use a lot of statistics if you want to follow just one particle for a very long time. And so therefore in that case we use a different method, because the Soré coefficient is related to an effective force that acts on the colloid that is named the thermophoretic force. And the Soré coefficient is proportional to this effective force of the temperature gradient on the colloid. And we measure this force by attaching the colloid into a harmonic potential and measure the elongation of this potential. And here is an example of a measurement in which we measure the force over a certain time until we have a stable signal for the forces. And here you see the force in the direction of the temperature gradient is clearly a different signal than the forces in the neutral direction, so to say. And here, this is already in the integral over time, so to say. So you sum up all the contributions to the force, because if you would measure at each time point individually, this signal would fluctuate much more strongly. So it would the fluctuations of this particle here, it does not get elongated in one direction and then fluctuates a little bit, but it fluctuates strongly around its fixing point. And therefore we have taken the average. And this is also the average over 20 different simulations, 16 different simulations here. This method had been used before in molecular dynamics simulations, where they also use the same mechanism to measure the thermophoretic force. And to verify that we don't have any additional effects due to the confinement of the particle, we we compare these simulations into a system where you let the particle move freely in the system. And there we measure the effective drift velocity. So after a certain time the colloid has diffused and then drift to a certain extent. And then the Soré coefficient, you can say that it's proportional to the drift velocity. And here is an example simulation which is taken over a shorter period of time, because if we want to let the particle move freely, we don't want it to reach the boundary of the system. Therefore, we restrict the simulation time to shorter time so that we are still far away from the boundary of the system. But to compensate for that, here we take much more simulations to average the signal. So this is here almost 2,000 simulation, the average of 2,000 independent simulation runs. But what you observe in both cases, if you compute the Soré coefficient, you have the same Soré coefficient for the same setup, and no influence of the confinement. Okay, so this is how our simulations are.
I'm sorry.
And what we want to observe first is the influence of the average temperature of your suspension. And here you see experimental data where you have the Fourier coefficient versus the solution temperature, and which is very similar to the previous results with the concentrated system. At low temperatures, the colloids drift to the hot side of the system, and by increasing the temperatures, they will start to drift in the opposite direction. That means you have a positive Fourier coefficient. And in our simulations with repulsive interaction potential, we observe a similar shape of the curve. So we have an increase of the Fourier coefficient with temperature, but we don't observe a sign change. That means our colloid, in this case, always drifts to the hot side of the system. And if we have attractive, maybe let me first explain you how we can understand this. Here is the schematic view of the colloid in the temperature gradient and the density gradient of the solvent. And due to the density gradient, the pure number of interactions that you have on this side is much larger than on this side. So if these interactions are repulsive, the colloid is effectively pushed towards the hot side of the system. This, in the case of a repulsive interaction, is enough to drive the colloid always to the hot side. In the case of attractive interactions, we have an additional effect of the temperature gradient, because here you have higher kinetic energies of the solvent particles, so they can penetrate deeper into the potential. That means if they can interact on this side stronger with the colloid. And so first, when you have attractive interactions, first, due to the density gradient, the colloid is pulled, in this case, towards the cold side of the system. But if you increase the temperature, then eventually it's pushed to the... oh no, sorry, I explained this wrong. If you increase the temperature, this is where the repulsive part of the potential becomes more important. And then if you increase the temperature, the colloids eventually start to drift also to the hot side of the system. But as a whole, you have an interplay of the density gradient and the temperature gradient. Another important experimental fact that we want to analyze, so this previous result, it will maybe become more clear in the next slides. But here, now I want to mention another effect, which is the dependence of the Fourier coefficient on the particle size. And there is experimental data that shows for very similar setup two different dependencies. One is linear and one is quadratically. And these two different results were debated, and there was no explanation why it is different for the same setup. And now we did our simulations, and in our case it was, if we use different types of potential, in one case we observed a cubic scaling with the particle size, and in the other case a quadratic scaling. And so we also had some controversial results, but luckily we could explain them, fortunately.
So, what are the differences between the two colors, the two types of particles?
Here?
Yeah, the two.
This I explained. So the thing is, to explain this difference between the different potential, we calculated the thermophoretic force analytically, and this can be done by just integrating the interaction volume, and integrating all the force contributions of the individual molecules. So we have the local density of the solvent times the gradient of the potential. And it is important to know how the local density looks like, because it is affected by the temperature gradient, like it's a linear increasing density in the bulk, but it's also modified due to the presence of the interaction potential. And additionally, we have to take into account the local temperature at each point here. And here I show you so to say, the average over all the interaction area in which the local temperature doesn't play a role, but this is just the effect of the potential. And here, if you have a repulsive interaction potential, you find that you have a decreasing density towards the core of the colloid. And this equation can agree perfectly with the simulation results. And in the case of an attractive potential, here close to the colloid, you will have an increased density of particles. And we plug this density together with the local temperature into this integral and compare this to our simulation results. And we find that here are the theoretical calculations with each of these points is. So this integral, you cannot solve it analytically, but you must solve it numerically. Therefore, we have each of these points here, and the curve is a fit to these points. And we find that we have a qualitative agreement of the theoretical predictions with all the simulation results. That means we have the same dependence on the diameter for different types of potential. And we also have the same temperature dependence. And in fact, we observed that this difference here between simulation and theory is approximately a factor of 2. But we cannot explain this factor, so that's why we do not collapse all the data and divide just by a factor of 2. Another thing that we learn from this analysis is that the Fourier coefficient, which is proportional to the thermophoretic force, is also proportional to the number of particles that interact in the colloid, with the colloid here. And this has an effect. So if you use different types of potential, this number of interacting particles will be different. So basically it's proportional to the surface area times the distance of the range of the potential. And if you apply a normal Lennard-Jones potential and you increase the diameter of the particle, you will also observe that you increase the range of the potential. So basically, this gives you effectively a cubic scaling of the number of interacting particles. And now, if we want to modify our potential, we use the potential with a constant interaction range, we find that the number of interacting particles is only proportional quadratically to the Fourier coefficient, to the number of interacting particles. And this is also true. So the same scaling you will have for the Fourier coefficient. So still, this is different from what is observed in experiments, because there you had a linear or a quadratic scaling. But as I mentioned with the introduction of the model, you have slip so the fluid can slip along the surface of the particle, and it is assumed that this slip, or it has been shown in another theoretical analysis, that with slip boundary conditions you would have a quadratic scaling, but if you have stick boundary conditions, you would have a linear scaling. And this is finally an explanation why we don't have the same behavior as we have in experiments, or it's what we assume at the moment. So this is already the end. So let me summarize what I have presented you. So I have presented you a mesoscopic method to implement the solvent, and this method is called multi-particle collision dynamics, and we have used it for the first time together with temperature gradients. And first we have studied concentrated suspensions, where we study the collective Fourier coefficient, and we have observed for different interaction potentials that the Fourier coefficient decreases by increasing the volume fraction, and that it increases for stronger attractions. And we find that we have a qualitative agreement with the experiment. And in dilute suspension, where we observe effects of the single particle Fourier coefficient, we have used an explicit colloid-solvent interaction potential. We study the temperature dependence and find that repulsive particles always go to the hot side, and attractive particles you have a sign change so that they go to the cold side for low temperatures and to the hot side for high temperature. And we observed that the size dependence of the Fourier coefficient can be explained by the scaling of the number of interacting particles. So, thank you for your attention.
Thanks for your talk. So I don't know if anyone of you would like to ask
in the case of the collective coefficient, how many particles there are in a simulation, in a typical simulation?
So we have approximately 1,000 colloidal particles.
And the kind of computer do you use?
So this has been done on single computers, so not in parallel.
So it's kind of really cheap, the calculation with PC.
Yeah, I mean, if you start a lot of independent simulations.
No, I mean, but I mean, just a single one is not like, for instance, like this Boltzmann or this kind of other methods where it's kind of
but
heavy
you still have to wait for 1 week or so until you have one data point. So.
And the second question was, in the single particle, when you study a single particle, you were showing this factor 2 deviation between one and the other, and so how you take into account that the force is also acting on the solvent and changes the distribution? This is not taken into account.
I can show you a nice figure which has been done by my colleague. He was also a postdoc at the same time, and he has studied the flow field which is around the colloid. And you can observe that you have, so to say, so this has been done together with walls, but in principle you have the same with, if you don't have the walls, with this biperiodic simulation box. And you have, so the force that is put here on the colloid also puts a force on the solvent, and that's it. Yeah,
kind of
in the convective motion move around the colloid.
And that could explain that.
Yeah,
Well, this is not taken into account in the theory when
Yeah, so this theoretical explanation is only local equilibrium. And we don't include that solvent particles have a velocity and carry momentum by themselves. So.
And have you checked your results in comparison with other hydrodynamic methods? Kind of
yeah,
one single particle you can compare also maybe with those tensors and this kind of.
So there was one
with the, for instance, with BTD or with lattice Boltzmann, maybe just a single particle. That should be
we have compared it to existing simulations with molecular dynamics and
with hydrodynamics or without.
Yeah, molecular dynamics. In principle, it should also have hydrodynamics. So, okay, if you would have to wait for a very long time, maybe. But,
you were comparing and things were agreeing.
in the molecular dynamics simulations, they compose their colloidal particles by many small single monomers, which they connect by beads. And
so you were doing, you were doing so with explicit solvent particles, and so molecular dynamics in the full with the solvent particles modeled as water or whatever.
yes. So I mean they also use this Lagrange interaction, but in principle they have a colloid which has internal degrees of freedom. So their intention originally was to study the conductance, so how does the colloid affect the conductance of the solution. Mm-hmm. In the end they focused on studying the Sorel coefficient, and of course if you have these single monomers composed of them, then you have also these stick boundary conditions, and therefore they also observed a linear increase with the Sorel coefficient. But they also used only attractive interactions, so they didn't study different interactions or so. They were, yeah.
Okay, so thank you again.
Sometimes we call it the molecular dynamics, but what we do is Langevin dynamics. By abuse we call it molecular dynamics. So for that, when you were saying molecular dynamics, I was thinking what we usually do that is this kind of Langevin dynamics.
Yeah,
but with the solvent and that's okay.
And you include the hydrodynamics with the kind
No, well, because what we do is kind of explicit. Implicit solvent. So you go with implicit solvent, and then of course you have to introduce those intensors, or you have to do this kind of DTV, or you have to do some kind of sort of things.
Mm.
But of course, if you model exactly the molecules, and so you do a kind of atomistic MD simulation, and you don't need any of these things because they are there. And then of course it's very huge to move and just well with the single particles still you can do with single color probably still what is the size and the water box is more or less small and still you can move it. No, but all what we do is with implicit solvent. It is true that sometimes this kind of molecular dynamics, we call it to the Langevin dynamics. So the thermostat, well, the thermostat is also what I mean. With that, it's implicit solvent. thermostat that is just simulating the peaks of the solvent. And